All right, so next we'll do 11.9, which is about representing functions as power series. And so what we mean by this is, let's look at an example, the one example that we already know. So last time we talked about the power series summation of x to the n from n equals 0 to infinity. This is just a geometric series. We know what its value is. So if x is absolute value less than 1, this thing is a convergent power series, a convergent geometric series. And its formula, the sum of this power series, is given by 1 over 1 minus x. So the r, the geometric series, the r is just x. So that one in the denominator. The initial term is when n equals 0 in the sum, my term would be x to 0, which is 1. Okay, so what we can say then is when this power series is convergent, and we know it's right here on this interval, when this power series is convergent, as a function, this is the same function as 1 over 1 minus x. So, in other words, let me just rewrite it, but say the same thing, but from a slightly different perspective. 1 divided by 1 minus x can be represented, or is represented by the power series, this. On the interval -1 to +1. Okay, so what we want to do, or what we would like to do, is for other functions, for other formulas like this, we would like to find power series that represent those functions. Because as we'll see a little bit later in this lecture, having a power series representation is nice because a power series is basically just an infinite polynomial. And what do we like about polynomials? They're very easy to take the derivative. They're very easy to take integrals, or to anti-differentiate. So if we have a complicated function, this was not that complicated, but if we had a complicated function and we want to integrate it somehow, it may be difficult or impossible to do it from the rules that we know from chapter 7. But if I turn it into a power series, integration is now very simple because it's just a polynomial. Okay, so that's the motivation for what we're doing here, is we want to turn functions into infinite polynomials to make certain things possible or easier. Okay, so I just erased it, but I'll write it up again. But you'll want to have in front of you the power series that I just erased. 1 over 1 minus x, it equals the summation of x to the n from n equals 0 to infinity if absolute value of x is less than 1. So this is like our basic power series. We can use it to figure out a lot of other power series. So for example, suppose I had the function 1 over 1 plus x squared, and I want a power series representation for that. Well, as a function, this is the same thing as if I took this function and plugged in negative x squared in place of x. So minus x squared is just 1 plus x squared. So this thing is this function with this expression plugged in. So what I can do is I can use the power series representation for this function, but plugging negative x squared in place of x. So all I'm doing then is taking the summation of, in this x here, I'm going to replace with minus x squared. Now we'll simplify that a little bit, but for this to be the same, whatever I'm plugging in for x has to satisfy this condition here. So this only works, this equality here, this only works if my input, negative x squared, has absolute value less than 1. But I mean, that's the same thing as if I took a square root of both sides, I need absolute value of x to be less than 1. So it didn't change my convergence requirement in this case. But we use this formula and this condition to derive both the new power series as well as the new radius or interval of convergence. Okay, so then I can simplify this to make it look a little bit more like a traditional power series. This would be negative 1 to the n times x to the 2n. And if you like, let me erase it to give myself room. If I want to now think of this as what does this look like if you were to write it out. If I just plug in the first few n's here. When n is 0, I get 1 times x to 0, so 1. When n is 1, I'll now have negative 1 to the first, so that's a minus sign. But it'll be x to the 2 times 1, so it'll be x squared. So what I'm going to get is an alternating sum of even powers of x. I guess next would be minus. Okay, so all these power series representations that we're going to be coming up with, just keep in the back of your head that they actually represent these infinite polynomials. So if I wanted to take a derivative of this, just think of it term by term. Each term is just a power rule. If I want to take an integral of this, each term is just a power rule for integration. Okay, so we'll do some more with that a little bit later. All right. Let's do another one. So I'll leave this up here for maybe one more example, but you'll want to have this for reference as we go. Okay, what if we had the function x squared over let's do 8 plus x cubed. Yeah, we'll see how this works. All right, so this is my basic power series that I want to use. So I want to make this look something like this. So one problem is on the bottom, I don't have 1 minus something, I have 8 plus something. So what I'm going to do first is let's factor out an 8 from the bottom. Right to the 1/8 times x squared over, this would be 1 plus x cubed over 8. Okay, actually, we also have a problem. The top is not 1, it's x squared. So let's pull that x squared out in front like this. So I'll have x squared times 1 on top. So x squared over 8 times this fraction. Now this fraction by itself, the second fraction, that's very similar to the previous problem. I can now think of that as 1 minus negative x cubed over 8. And so now this fraction is just like plugging in negative x cubed over 8 in place of x. So I can take this fraction and I can write it as a power series, just like the previous problem. Now the x squared over 8, I don't have to worry about that really, because that's already a polynomial. I don't care about making a power series representation for a polynomial thing, because that's already a polynomial. The point of making a power series representation is to write a more complicated type of function as an infinite polynomial. If it's already a polynomial, like x squared is, it doesn't need to be written as a power series. You just leave it separate. We'll worry about it in just a second. Okay, so what I need to do then is keep the x squared over 8, but now we're going to replace that second fraction with a power series given by replacing x with negative x cubed over 8. So negative x cubed over 8 to the nth power. So whatever takes the place of this x takes the place of this x. And for that replacement to work, we need this input to satisfy this condition. So we need absolute value of negative x cubed over 8 to be less than 1. Absolute value is going to get rid of the minus sign, so I can ignore it. If I multiply both sides by 8, I get absolute value of x cubed is less than 8. If I take the cube root, I get absolute value x is less than 2. So there's my new radius of convergence, my radius of convergence for this power series. Okay, so I'll erase this condition in a second to give myself a little more space, but now let's simplify this. So this will be negative 1 to the n times x to the 3n divided by 8 to the n. Now we still have this stuff outside the summation, but I can multiply it into the summation. This is just like, I have a big sum, a bunch of stuff being added together here. It's all times this. So I can distribute this extra factor out front. I can distribute it to each term in the sum. So what happens then is, if I want to write this as a single summation, x squared gets combined with x to the 3n to give me x to the 3n plus 2. X to the 3n plus 2. And if I want, I can multiply this 8 times 8 to the n to give me 8 to the n plus 1. So there's my power series. Its radius or interval of convergence is right here. Its radius is 2. All right, so if our function that we're trying to write as a power series is similar enough to this kind of expression, we can factor stuff out and figure out what needs to be plugged in place of x to turn this into a power series. But we can do more than that. That'll get us so far. Let me state the important theorem here, or let's just say what it tells us. I'm not going to write it all up, but a function represented by a power series with a positive radius of convergence. So I'm going to use capital R like we did before, but it needs to be positive. So it can't be a 0 radius of convergence power series. can be differentiated or integrated term by term. So this is just what I was saying earlier. If we can write it as a power series, it's like an infinite polynomial. I can then go through and take the derivative of each term separately to get a new power series, or I can take the antiderivative term by term to get a new power series. So we'll say that it can be differentiated or integrated term by term. The new power series will have the same radius of convergence. And here I want to emphasize radius. So if the original power series I started with had radius convergence 1, for example, if I integrate it or take its derivative, I get a new power series. Its radius will also be 1, and its center will be the same as well. The center and radius will be, say the same, but the interval might change at the endpoints. So you might lose convergence at one or both endpoint potentially. Okay, so let's do this on some examples. All right, so let's start with our favorite example, or our basic example, 1 over 1 minus x. That is, let me give myself more space here. Okay, so I want to write its power series. Let me write it over here. So it's summation of x to the n equals 0 to infinity. So if I write that out, though, term by term, if I just write that out for a few terms, that's 1 plus x to the first plus x squared plus x cubed, and so on forever. So let's take the derivative of this. So the derivative of this function would be, by the chain rule, we're going to end up getting 1 over 1 minus x quantity squared. The minus signs would cancel. 1 from this minus sign, 1 from the negative 1 power. We get this function if we take its derivative. Now if I go through this infinite polynomial and take the derivative, I'd get 0 plus 1 plus 2x plus 3x squared, and so on. That's going to go on forever. If I do it to the generic term, the derivative of x to the n with respect to x would be the power comes down n times x to the n minus 1. Now, I have a problem. If I start my sum at n equals 0, then technically I'm going to start to have a problem with 0 minus 1 here, and again, negative exponent, that's bad. But that's because my constant term from the original series, it disappeared, and my new constant term is here. So I can deal with this one of two ways. I can start my sum at n equals 1, because then this exponent will be 1 minus 1, which would give me 0 power, or this. So I could write like this. That's fine if you want to write like that. You could also renumber things to make it start at 0 if you wanted. So what I need to do then is replace n by n plus 1. So if I start at n equals 0, then my first term is going to be 1 x to the 0. So I'm adjusting my index basically by replacing n with n plus 1. If n plus 1 equals 1, that means n is 0. and I have n plus 1 and n plus 1 minus 1 here. That gives me n plus 1 x to the n. These are the same series. One's not better than the other. Either one is fine. Right, but in any case, whichever one I like, I'll just use the first one since I didn't have to do so much manipulation. That's a power series representation for 1 over 1 minus x squared. Its radius of convergence will be the same as it was here. So if absolute value of x is less than 1, this equals this, and that means when absolute value of x is less than 1, this equals this. Okay, let's do another one. All right, let's do this deliberately here. Let's do an integration one. Let's do 1 over 1 plus x. Now that's the same thing as 1 minus negative x. So I'm just plugging in negative x into my other power series. So this would have power series negative 1 to the n times x to the n. If I plug in negative x into my standard power series, that's what I get. Now if I write this out, I would get 1 minus x plus x squared minus x cubed, and so on. So now I want to integrate this. Integral of 1 over 1 plus x, that's just a simple substitution. That's ln of 1 plus x. I guess I use absolute values here. So ln of 1 plus x. Absolute value of 1 plus x. Now, if I integrate this term by term, 1 turns into x. So I would have x minus integral of negative x would be minus 1 over 2 x squared. Integral of x squared would be plus 1 over 3 x cubed minus 1 over 4 x to the fourth, and so on. Generically, let me do it underneath. Generically, I want to integrate this general term. Negative 1 to the n, that's a constant. We're integrating with respect to x. So it's really just a power function of x. So that'll be x to the n plus 1. I have to add 1 to my power and divide by the new power. So I still have negative 1 to the n because that's just a constant multiplier. So negative 1 to the n divided by n plus 1 times x to the n plus 1. And again, this will start with n equals 0. If I do that, then my first power of x is actually 1. When n is 0, I get x to the first. So this doesn't have a constant term. Now there's one issue we need to think about. We're integrating. This is just an indefinite integral. And when we do those, we want to put a plus c, right? But if I'm after the power series representation for this specific function, I want to make sure that when x is 0, I get the correct constant term for my polynomial. So when I integrate these, I should do it like this. Stick my constant term at the beginning, c plus, and then do my integration term by term. So integral of 1 is x, of x is 1/2 x squared, etc. So stick my unknown constant at the beginning, and then figure out what should that constant term be for this specific function. And so I figure it out by plugging in this case, x equals 0 would kill off all of these higher degree terms. If I plug in x equals 0, that should give me the constant term. Okay. If it was centered someplace else, like x minus a number or whatever, then I'd plug in the center. But in this case, what is this function when x equals 0? I'd have ln of 1 plus 0. ln of 1 is 0. So that tells me this constant term should be 0. So it's really this. This is the power series representation. I'd stick the c in front, but then I figure out c is 0, so in this case it's gone. Okay, so I have a power series representation for ln of 1 plus x now. And its radius of convergence, again, since I didn't do anything too drastic to my original power series, this is still convergent when x is absolute value is less than 1. So when I integrate one that has a radius of 1, the new power series will also have a radius of 1. Okay, so rather than do too many more examples like this, in the textbook, it has some other similar examples of figuring out what are power series representations for other sorts of functions. There's also a table. I have to double check. There's a table either in this section or the next section for a list of known functions. But let's do some examples where we illustrate using this. All right, so here's a question. I'm going to write an integral here, but I want to integrate it using power series or as a power series. Okay, so we'll do a few of these, but suppose I wanted to integrate the function x divided by 1 plus x to the 7th power. If that was all I wanted to do, theoretically we can integrate this. This is a rational function. If you go back to chapter 7, we technically know how to integrate any rational function. We can integrate rational functions using partial fractions decomposition. Okay, so we could do that. The problem is, to use partial fractions, I have to completely factor the denominator into its irreducible factors. 1 plus x to the 7th, that's going to be a pain. I have to break it down into linear and quadratic factors. Okay, so it's possible, but that's kind of beyond the scope of what we did in chapter 7. All right, so instead, I want to turn this into a power series, because integrating a power series is easy. Once you get a power series, the integration part's very simple. All right, so let's turn this into a power series. This is similar to our first couple examples. We have an x on the top, so let's pull that out. 1 plus x to the 7th is the same thing as 1 minus negative x to the 7th. So I write my function as something that I can turn into a power series. This would be summation, so keep the x, summation of negative 1 to the n times x to the 7th to the n. Okay, I just plugged in negative x to the 7th into my basic power series. So I got a negative 1 to the n and x to the 7 to the n. Whatever's inside here becomes something to the nth power. Okay, so let me put the next step up here next. Okay, now I want to simplify this. So let's simplify the inside of the series. We have negative 1 to the n times x to the 7n. Then I want to multiply this x into that power series. So that's just going to add 1 to my exponent on the x. And so there's my power series representation of the integrand. Now I'm ready to integrate. It looks intimidating before you get used to these, but that's actually a very easy integral. It's just a polynomial that goes on forever. So the way I integrate it is, when you do these power series integrals, start with the unknown c. Just put c plus, and then you have a sum. You have a sigma. It's going to have the same starting in value as the original. And now my summand, the thing I'm adding up, it's just a coefficient times a power of x. No matter how complicated it looks, this is always a coefficient times a power of x. So anything that doesn't have an x, that's a coefficient, you keep it. So negative 1 to the n. Then you have a power of x. You integrate it by adding 1 to the exponent, so it becomes x to the 7n plus 2, and then you divide by that new exponent. So 7n plus 2 in the denominator. And, I mean, as far as what my question was, we're done now. We got the answer to the integral. We got our antiderivative as a power series. Okay. Now, hypothetically, if we went through the trouble of integrating this thing by partial fractions, and we went through all that ordeal and got to an answer, that answer's power series representation would be this, or could be represented by this power series. Okay. This was a lot easier. Now, this way of writing the answer has its advantages and its disadvantages. A disadvantage is it's not so easy to compute this, to plug in an x value and get an answer for this function. Because you have to find the value of a convergent power series. Let's get out of the way. The advantage, I guess, is it was much shorter to get here. If we were going to use this to do a definite integral, if we need, so let me start again. If we needed to use this to compute specific x values, like for example, if this is a definite integral and I need to plug in x values to this, then at least for this example, since it's an alternating series, we talked a little bit how we have a fairly easy way to approximate the values of an alternating series. But that's the trade-off. It's easier to integrate. The outcome is not as useful as the outcome from actually integrating it with our integration techniques. But that's all we can do in some cases. So in this case, we had other options, but that's not always true. So for example, let me do another one that. Okay, so what do I want to do here? Okay, so maybe maybe as a prelude to the next example, let me do one more derivation of a power series representation. So suppose I wanted to know what is a power series for arctangent of x. So I want to know what is this power series. Well, I need to turn this into something that's similar to one I already know. Well, if I take the derivative of this, I get 1 over 1 plus x squared. This is close enough to our basic power series that we can write it out. So this is 1 over 1 minus negative x squared. So that's negative x squared to the n. And so if I clean that up, that's negative 1 to the n. I guess this is close to one that we started with, isn't it? Negative 1 to the n times x to the 2n. So that's the power series for the derivative of arctangent. Therefore, the power series for arctangent will be the integral of this, the antiderivative of this. So I'll put a c plus, and now anti-differentiate this. Again, negative 1 to the n, that's a constant multiplier. So you keep that. We'll have x to the 2n plus 1 divided by 2n plus 1. And now what is c? Well, if I plug in x equals 0, this power series only has positive powers of x. So if I plug in x equals 0, the power series disappears and I'm just left with c. So arctangent of 0 is, so c equals arctan of 0, which is 0. So the c disappears. And there we have one more power series for some other type of function. Okay, so keep that in mind. I'm going to refer to it. But now suppose I wanted to integrate I guess I'm wasting so much space here. Arctangent x divided by x. So suppose I wanted to integrate this. Well, just at a glance, if I wanted to try to do it with an integration technique from chapter 7, my best bet would be integration by parts. I have a power function and I have a arc function. So I try to do integration by parts. That's not too promising though. Yeah, it seems like it's going to be bad. Maybe it would work though, but it doesn't seem like it'll be easy. But now we know arctangent can be represented by a power series. If arctangent got replaced by a power series, I could divide x out of it and still basically give me a power series. Once I check a couple things about the exponents. But if we know a power series for arctangent, and we have other x's multiplied or divided, that gives us a way of trying to make the whole thing a power series. Okay, so let's do that. Let's turn this into a power series. Let me run 1 over x out front. Summation of arctangent x. I just erased it. This was negative 1 to the n times x to the 2n plus 1 divided by 2n plus 1. Yes. N equals 0 to infinity. Okay. So it's not ready to integrate just yet because we have this extra x that's not part of the series. So we need to turn it into a single power series where it's just a infinite polynomial. That means I have to multiply this 1 over x times x to the 2n plus 1. All that's going to do is subtract 1 from my exponent. So rather than rewrite the whole thing, I'm just going to erase. Dividing by x is going to decrease the power by 1 on x. So this will become summation of negative 1 to the n times x to the 2n divided by 2n plus 1. All right. So now once you get to this stage where it's integral of summation of a power series, the integration is now simple. So we're going to integrate. This equals, integrate a power series, start with the constant, so c plus, then you'll have a summation with the same starting n value. Everything that doesn't involve x is just a constant coefficient. So negative 1 to the n divided by 2n plus 1. That's just a coefficient, so write that first. Then integrate that power function. X to the 2n becomes x to the 2n plus 1. You're adding 1 to that exponent, and you divide by this new exponent. So we can write like that, 2n plus 1 squared in our denominator. Okay, so let me just try to clarify one more thing. So the constant, the c we put here, when I write that c plus at the beginning, that's just like whenever we did problems from way back where we're doing an indefinite integral. Integrate this function. That means you're trying to find the general antiderivative, which means the entire class of families that serve as antiderivatives for that function. And for those, you have that unknown c value. Contrast that with the few examples I did where I was figuring out what was the power series for arctangent, or what was the power series for ln of x plus 1. There we had a specific antiderivative of some other function. And so for that specific antiderivative, it has a specific value for the c that we had to figure out. So arctangent of 0 was 0, so its c value was 0. Here, I'm not looking for a specific antiderivative. The integral of this means the general antiderivative, so it should have a c at the end. In our final answer, there should be a plus c that we just don't have an answer for. Okay. It's only when I'm using integration to figure out a new power series from an old power series. I figure out the power series for a specific function that I need to figure out what specific value of c to use. Okay, so I hope that made some sense. All right. So that about wraps up section 11.9. I'll put a few problems at the end of the video here. We have one more section from chapter 11 I want to cover, 11.10. That'll be the next video. The idea there is, in general, if I have a function and I want a power series for that function, how can I come up with a new power series for a function if it doesn't directly come from one I already know? So I can only do so much with summation of x to the n, or 1 over 1 minus x. I can only do so much from that. I can do things that are similar to it. I can do things that involve arctangent or ln because those relate to things of that nature by integration. But like e to the x, I can't get that from 1 over 1 minus x, or sine x, trig functions. I can't get that from 1 over 1 minus x. So the next topic is to explore what do power series look like for other kinds of functions. How do we figure them out?